Okay, off we go. Here's what we were talking about last time. We were doing change of variables. I kind of introduced the broad brushstroke big idea of change of variables, which basically was to take a certain point of view, kind of a more geometric point of view on good old-fashioned substitutions from Calc 1, right? And then just try to do the same kind of thing in a two-dimensional context. And big idea, again, is that if you have a function, wrong pen mode. If you have a function that gives x and y as functions of u and v, well, you can plug that right in. There's no tricky curves on that. Just whatever x is as a function of u and v, plug it in, no problem. And then the only thing that's a little tricky is you have to remember to keep track of how du dv is not the same as the area of its image in the xy plane. So areas are going to get stretched out. There's some factor by which the area on the left is stretched to produce the area on the right. And you just have to insert what that factor is so that you'll have a reasonable formula, a valid formula for your, dx dy. That would be, at the end of your xy integral. Okay, so plug in and don't forget your stretching factor is the sort of executive summary of how to do this. Okay, now what is the stretching factor? This is where we left off last time. So how are we going to compute that stretching factor? Can I just cite a derivative? Not that simple, right? Because this is now an area. I can't reinterpret an area as a change. That's not on the table. So here's the thing. I'm actually not going to show you why the following is true just yet. There is enough going on at the moment, just keeping track of how this process works, that I don't want to get distracted by formalities. So I'm going to, for the moment, just make a claim, and then in a few minutes, I'll justify the claim. So the claim is that stretching factor is this formula right here. It's the absolute value of the determinant of the derivative matrix for your change of variables function. That's the formula. All right. Now, quick reminder, don't forget the derivative matrix is this matrix of partial derivatives right there. Turns out, and I think this is pretty believable, if you look at this determinant, let me just kind of think out loud about what we're looking at as the determinant. The determinant is a scalar. So this thing that I have highlighted in purple is a scalar, and it's a scalar that's heavily involved with all the partials of x and y with respect to u and v. So how about this? This seems like a not implausible choice. It almost reads as partials of x and y with respect to u and v. And writing it as a fraction, it makes it look like a scalar, and of course determinant is a scalar. So, not the craziest choice of notation. Now, is it a fraction? Oh no, not at all. It's not a fraction. I'm writing it as a fraction, sloppy though that is, because it turns out it behaves like a fraction in a couple of different ways. And let me show you the first way that this thing actually does behave like a fraction. Let's take this formula for the stretching factor, and let's actually plug it in. Right here in our original formula, where it's supposed to go. So here we go. Let me write this down. Absolute value, partial xy, partial uv. And keep in mind that is what we multiply by our input area, du dv. Presumably, hopefully, to get the output area, which one might reasonably write as dx dy, representing area in the xy plane. And so the hope is that what I have in blue on the left would be a reasonable suggestion of dx dy. Now, is that a reasonable suggestion? Well, now again, this is total crime, and I get the willies just thinking about it, right? But it's almost like that and that cancel. Now, they don't, because that's not a fraction. And this thing in the denominator is not a thing, right? This is an abuse of notation. but it's as if they cancel, and the result is as if I get dx dy. So there's something kind of satisfying about this little, notation crime. It's quite convenient to just write it that way. Okay, so heads up about that. That's why we write it like so. All right, let's do an example. Now, this is a highly manufactured example. This is not representative of what you're going to see when you do change of variables problems. This is just to get the ball rolling. We want to get one into the win column, right? So I'm going to give you a bunch of free information in this example. Again, just to get the ball rolling. Okay, so we're doing an integral on some domain in the xy plane. That claim ends up looking like this. Specifically, what is that domain? Well, it's the image of the unit square in the UV plane. Here's the unit square in the UV plane. And specifically, being the image, it's the image by way of a function which I'm giving you. I'm giving you this change of variables function g. And the blue is the image of the green. And just as a reminder, that's exactly the scenario that we entertained here. And let me clean up the mess. There's a lot of junk down here. That's exactly the scenario we entertained here, that we were looking at an integral on a domain that is the image, it says right there, image by way of some function g of a domain there. So this is the perfect setup to use our brand new change of variables formula. All right, now again, let me just confess again, this is highly manufactured. This is not going to work out most of the time in practice. Most of the time, you're just going to have some domain, and that's it, right? So here, the way I phrase the question, you get to infer, kind of for free, what your change of variables function is. There it is, given. That was nice, right? And you also get to infer what your pullback domain is. And keep in mind, the big idea of change of variables is that I'm going to take the integral that I was given and rewrite it as a different integral in the UV plane, effectively going backwards through the function that goes forwards. So again, I like to call this a pullback, and I like to call this new domain that I have in green here, call that the pullback domain. Okay, so again, perfectly set up for this. Now, all we need in order to be able to make this work is the stretching factor. Let's see here. I just need to compute this stretching factor for insertion as indicated. That then is what I need to compute. So off we go. Let's compute. Oh, and let me keep that on the screen here. Let's see. So yeah, we have our change of variables function given. We'll start with the Jacobian determinant right there. Details. Make sure that you understand where this matrix came from. Again, that's the derivative matrix for x and y as functions of u and v. Take the appropriate partials. Don't get your rows and columns confused. Lucky break, it happened to be symmetric in this case. You won't always get that lucky. And then this little fractional notation means determinant. Okay, and that's an easy determinant to compute. Now, here's where it gets a little unfortunate, a little annoying, and that is that this thing is not my stretching factor. I need the absolute value of that thing. How do I compute the absolute value of some weird expression that isn't immediately obvious whether that's positive or negative? Right? And so you have to break it down and analyze the expression in question. You can't just throw away the absolute values. That's no fair, right? So here's the good news. Good news is what we're going to do with that expression is actually right on the page. It's actually looking at us right now. And it's right here in this picture on the left where I can directly answer the question of what's the deal with u? What can I say about u? Well, here it is. There's u, and apparently on my domain, u is always between 0 and 1. I can see it in the diagram. Is that cool? Everybody's happy? Okay. Likewise, now I'm going to apparently need to know something about v. What can I conclude about v? Well, on my new set, there's v, and it would appear it's always between 0 and 1 also. So I actually have everything that I need. If I want to understand how to take an absolute value of 4uv minus 9, well, u and v, right there, u and v are always between 0 and 1. That means 4uv is always less than 4. When you subtract 9, definitely negative. Is that cool? Everybody's happy? Okay, yeah.
Could you please repeat that explanation?
I can't hear you, I'm sorry.
Could you please repeat that explanation?
Okay, u is always less than 1, v is always less than 1. This product is always less than 4. Less than or equal. You subtract 9, it's going to be negative. Yeah. Okay. All right. So, okay, now the last little bit, how do you take the absolute value of something that we know is negative? And so I hope everybody's good with this kind of thing. The absolute value of something that you know is negative is the negative of that thing. Right? So something to think through, but anyway, the absolute value of that expression then is like so. Yeah?
So if you didn't know u and v were like in between 0 and 1, would you just leave the absolute value bar as your answer?
And it would be inside of your integral, and then you would have an integral to evaluate that had absolute values, and there's no way to do the integral without actually figuring out where is it positive, where is it negative. Yeah. So you really kind of can't get around it. Yeah.
Yeah, we're kind of always using unit squares, so.
Oh no! This particular example,
okay.
Yeah. Okay. So now, in my general thing here, I drew it as always being a rectangle. But again, you don't even have to do that. I really what I should have done is I should have just I don't know how to indicate that the goal of all of this is just for this pullback domain to be more desirable, less ugly than whatever that is. So yeah. Right. Okay. So. Yeah, now it's just a matter of plugging in. Now there's a couple little details to keep track of. So let's not lose sight of the fact that we just computed our stretching factor. Our stretching factor is a new factor to be inserted, goes right there. Arguably the most important part of the problem is to include the stretching factor. But then there's also the rest of the integrand. This integrand, I wanted to use green for something else. This integrand right here, or the former integrand, you got to rewrite that as well. And here's the good news. X, what do I do with that x? How do I rewrite x in terms of u and v? Change of variables function, right? The change of variables function literally gives me x's and y's in terms of u's and v's. And I can see it right here in the formula. X is that expression right there, and so this x is just that. Everybody happy with that? So that's the easy part. That's just plugging in. Just don't forget to actually do that. Okay. All right. Now let's try to post game this. Was this a good thing? Is this a bad thing? Oh yeah, question.
Back to the question about like a non-specific domain where you don't know if like u and v is like greater than or less than like 9.
Yeah.
With the absolute value, couldn't you just like break it up into like two cases?
Totally.
If you have like a indefinite domain.
Yes.
Okay.
That is exactly how you'd proceed. Yeah. Yeah, you'd have to break it. You've probably seen single variable calculus versions of this where if you have an absolute value, then you just look at your integrand, you see where is it positive, where is it negative, you just break it up into two separate pieces. Yep. Okay. 100%. Okay, so was this a win? I say this was a massive win. Now, you might not think so because, here was our original integral. That's a pretty nice integrand. Here's my new integral. That's not as nice. I mean, again, at a casual glance, nobody's picking the green integral, but what you got to remember is the green integral is computed on this domain, which is just a square. It's, in fact, the unit square. It's the world's easiest domain for a double integral. Can't beat it, right? It's awesome. Whereas this blue integral that I started with, again, don't forget the image was this wacky thing here. And now think about how you would break this up as an iterated integral. And you're going to slice through corners, no matter which way you go. dx, dy, dy, dx, either way, you're slicing through two corners, which means it's three separate integrals. And we don't have the equations for these edge curves yet, which means you've got some algebra to do to even figure out what these edge curve equations are and then solve for the blah, blah. There's a fair amount of tedium that goes into that blue integral. So don't get distracted by the integrand. The integrand is usually not the problem. The problem is usually the domain, and this has turned a bad domain into a good domain at the low cost of my integrand is a polynomial. Which again, not that bad. Is that cool? Everybody see the win on this? All right. Yeah.
So, as far as solving that, are we looking at like the area of this UV square?
It's not area. It's that this is my domain for this integral, and so I've got to rewrite this as an iterated integral.
Just of like you. Okay.
Yeah, it's just so it'll be 0 to 1, 0 to 1. And then, du, dv. Yeah.
And but the middle stays.
Yeah.
Okay.
Yep, that's right. So this is my new integrand. In some sense, what I have on the left is just recopying the old integrand, and then this thing here is my stretching factor to make it all equal.
So do we have to distribute the stretching factor and then integrate?
I mean, the stretching factor is part of the new integrand. So you've got to treat it like any other factor. Yeah, it is part of the integrand. So yes. Does that make sense?
Yes.
Yeah. Okay. Yeah.
So this just now determines our new bounds.
Yeah, that's right. So 0 to 1 is this square is our bound. That's our domain for this new integral. Yeah. Okay. So now, again, this was a manufactured example. I gave you the change of variables function. Doesn't usually work out that way. Usually you kind of have to find your own change of variables function. There's different ways to do this. I'm going to show you an example of one of these, but I just want to start with the observation that a translation, right, now this translates by the vector a comma b. You've got to keep in mind, change of variables functions go, go that way. But we're ultimately pulling back. We're ultimately going the other way. So if this g function adds a certain vector, going the other direction will effectively subtract that back off. It's just undoing what you did. And so in effect then, this would be a good choice for a change of variables if what you want to do in the pullback to the domain is to translate by negative a, negative b. There's just kind of a backwardness to it. And so likewise, if you stretch in the x direction by a factor of k, when you pull back, you will effectively be squishing by a factor of k in the x direction. So just undoing what you did. And likewise with the direction of your rotation. If your change of variables is a counterclockwise rotation, undoing that will be a clockwise rotation. Okay, so let's see an example. I'm going to do a rotation example here. So just to get set up, our domain is a square, specifically with these corners, which is this square right here. By the way, nice little analytic geometry exercise. Persuade yourself. How would you do this, by the way, that this is actually a square? Yeah, think about vector addition and dot products and stuff like that. It's a nice little exercise. Okay, so that's our domain on which we want to do some integral, and I want to do I don't like this domain. I don't want to keep this domain. This domain is terrible. Because slice it up, right? Think about what would happen if you slice it up. You're slicing through corners. No way around it. You're going to hit 2 corners, whichever way you slice. You're going to have 3 integrals, therefore. And again, nobody wants that. Okay, so now let me think out loud. What would I like to do to this domain? And I tell you what I would like to do. I would like to rotate it clockwise, because if I were to rotate it clockwise, it would become a nice, parallel to the axes, pretty little square that's, constant bounds. Life becomes good. If I could only figure out how to rotate it clockwise. So what I'm going to do is I'm going to make my change of variables function rotate counterclockwise. Right? So if, in fact, what my t does is rotate counterclockwise, keep in mind that means that my blue domain then is the image of this green domain. In other words, if you take this green square, if you rotate it by our t transformation, if you rotate it counterclockwise, you get the image. You get the blue square. That is our actual domain. So again, there's kind of this backwardness to it. I wanted to take my given domain and rotate it clockwise, so I view it as being the result of a counterclockwise rotation. Does everybody see the backwardsness of that? Yeah, it's just you kind of have to think in those terms. Okay. All right. So, let me clean up the mess there, and I'm going to put that back like so. Okay, by the way, a little bit of geometry, and this is an exercise that y'all can do. This point being that point will allow you to do some trig and conclude that that angle is pi over 6, so make sure you can do that trig. And as a result, then, now I can write down exactly what my linear transformation is. This linear transformation, reminder, rotations around the origin are linear transformations, is represented by the matrix that is this. Now that's another linear algebra thing. Y'all remember I've said this a million times. I'll probably say it a million more. It's very important to be good at the following line of reasoning. Linear transformations are represented by matrices that can be understood by their columns, which are the images of the standard basis vectors. So what you're going to do, the way you're going to get this matrix, and again, it's very important that you can do this for yourself, take the standard basis vectors and rotate them and see what you get. And this first column is the image of E1. The second column is the image of E2. So good blanks to fill in. Make sure you're good with that. Okay. Okay, yeah, and then recognizing that our angle is pi over 6, this becomes that there. Okay, so all together then, our linear transformation is given by this algebra right there. And it gives x and y as functions of u and v. Everybody on board? Yeah.
Where did the transformation matrix come from, like with the cosine?
Oh, yeah, so that's what I was talking about with the linear algebra, and this is mostly an exercise I'm leaving for y'all. So what you want to do is make sure you, so take the standard basis vectors, rotate the standard basis vectors, do the appropriate trig, columns are those images. And so that's going to be, talk to me in office hours if you want more details. Yeah, right. Okay. All right. Okay, so let's see here. Stretching factor. We'll insert the absolute values in a moment. But this is most of the work of the stretching factor. And so you've got various partials to compute. Now the confusing part here is, wait a minute, what is x? Right? Where's my x? Well, you can see in the setup of the problem, x is the first output variable of your change of variables function. It's really easy to lose track of this, and a lot of students forget. But x, being as it is the first output, I can compute it literally as the first output of my change of variables formula. So this being a matrix vector product, just that dot product is x, and that's going to again give you that row, and then likewise y is the second output, which means y is that dot product, and its partials give you that row. All right? Everybody happy? All right. Okay. Now something weird has happened here. Golly, we had a bunch of trig and some square roots and some calculus, and after it's all said and done and the dust cleared, the answer was 1. Just 1? What a coincidence. Right? What are the odds? Well, this is actually very reasonable if you think about what's actually happening geometrically. The whole point to this is that we're just talking about a rotation. And when you rotate, rotations are a rigid motion, right? Nothing gets stretched. Nothing gets bigger when you rotate it. Right? Nothing gets smaller when you rotate it. So this kind of has to be the answer. Does that make sense for everybody? All right, so that's a good thing to keep track of. Now that said, just a point of policy. I do still want to see the calculation, like on an exam or on a homework exercise. Please do show me the calculation. Yeah, right. Yes.
Can you explain why it's expected?
Well, yeah, because it's a rotation, and when you rotate, things don't get bigger, right?
Right,
So.
but what about the original one? Shows us that it's 1.
The what now?
Like the S in the top.
The.
Yeah.
Oh.
S on the left. Like.
Yeah, so that's not the point. What we're interested in here is the factor by which, if you look at little pieces of area, how much those little pieces of area get stretched, and what we're computing here is that stretching factor. And the punchline is very simply, when you rotate things, their areas don't change. So they change by a factor of 1. Yeah, said differently. Yeah, right. Okay, so basically done at this point. Don't forget to put the absolute values on your stretching factor. Right? Doff the cap. It is an absolute value. And then it's just a matter of plugging in. And don't forget, x is, for example, that dot product. And so this x right there is just that right there. Does that make sense? Everybody's happy? Okay, so again, we have this, is this a win? Is this not a win? Which is better? And you look at these two integrals, and it's tempting to look at, wrong color, of course. It's tempting to look at that integral that we just produced and this integral that we started with, and to say, thanks but no thanks. I'll keep what I started with. Look how much smaller that blue integral is. And again, massive distraction, completely not the point. The only thing that makes this green integral a little less convenient is the constants are slightly aesthetically unappealing. Constants, right? But they're constants. Algebraically speaking, this is no worse than that is, but much better with the domain, right? We have a much better domain here, and that is way better than that terrible domain that we started with. That makes sense? Again, big win. Okay, couple of more little annoying details that have to get said. This is not going to be an issue at all, but just as a formality, I'll point out, yes, this function, change of variables function, does have to be continuously differentiable. Nothing to worry about in this class. Also, not really anything to worry about, but if you, at some point in the future, you might conceivably, it is important that the change of variables function be invertible. If it's not invertible, then bad things happen. And it has to do with the absolute values, and this is not something I want to spend class time on. But if your change of variables function is not 1-to-1 and on-to, right? The pullback domain and the given domain, if they're not 1-to-1 and on-to related by the change of variables function, then you're going to have a problem. So just keep an eye on that. Okay, moving along. So here's a weird fact. Sometimes your function's going to go the wrong way. Sometimes you're going to be looking to do a pullback. You're going to have some region over here that you don't like, and you're going to want to turn that into some new region over here that you do like, but you're going to find that your function is better thought of this way. And we're not set up for that, right? We are set up, the only thing that we have that allows us to do pullbacks, go way back to it here, is we pull, the term pullback is we're going backwards through the change of variables function. Stuff that are the outputs, we rewrite in terms of the inputs. Okay, so what would we do in a situation like this where the function, let's see here, where the function's going the wrong way? I don't want to pull back through this function. I want to kind of push forward through that function. And the answer is, it turns out the algebra still kind of works out. And it's just kind of a matter of plugging things in. One of the worries that you have to deal with is, how do I compute my stretching factor? And there's a lovely little argument as to how we can compute that stretching factor. And here it comes. When you have I'm going to say, good direction change of variables function, don't forget we take the partials of the outputs with respect to the inputs, of course. And there's that little fractional notation that we use for how to represent the stretching factor. Okay, so we take the partials of the outputs with respect to the inputs. Fine. Okay, well, yeah, but here's the thing. When you're going the other way, the stretching factor is the partials of the outputs, but now the outputs are u and v. With respect to the inputs are now x and y because our function is going the other way. All right, so these stretching factors we would have to write like this. And now I'm going to ask the question of, what if I do this like that? What if I take some little piece of area in the UV plane and see what the resulting XY points are and then convert right back into the UV plane? Nothing happens, right? I get the exact same little piece of area. Overall, how much has the factor changed? It hasn't changed. Factor's 1. Is that cool so far? Okay. Well, conveniently, as we just discussed, the push forward stretching factor is this, and the other direction, sort of the second half, if you will, the coming back the other way stretching factor is this. And so, check it out. These things that we have written in notation as looking like fractions, that look like they are reciprocals of each other, they are reciprocals of each other. It's super handy, right? This is yet another reason why I like this notation that writes it as if it's a fraction, which it's not, but it pretends like it's a fraction because it behaves like a fraction. Okay. So, very handy. Now, here's an example where this is going to come up very naturally. This is a classic first example of this kind of thing. I want to talk about where this comes from a little bit, but let me start with what it is. We have a couple of curves here, a couple of level sets of x, y, and a couple of curves here, a couple of level sets of x, y squared, and we're looking for the region that's bounded in between those curves. So that is a weird little region. Everybody see that? Okay. So let me try to persuade you this is not an entirely manufactured example. Someday, most of y'all, being engineers, will take a class in thermodynamics. When you take a class in thermo, you'll study something called the Carnot cycle or the Carnot engine. The Carnot engine is a theoretical engine that allows you to draw powerful conclusions about fundamental, basic properties of laws of thermodynamics. And when you study the Carnot cycle, there is a region that comes up in a very important way that is very, very similar to this. It's weird, but it looks a lot like this. Now, I've cleaned up the numbers just a little bit for streamlining. I don't want to get distracted with fractional exponents and annoyances like that. But structurally, morally, pretty much is this. So this is actually a very naturally arising shape. And we're going to entertain how to deal with something like this if you have to do an integral on that weird shape. So now there is a trick to this. I didn't think of this trick, and it is not expected that y'all will have been able to think of this trick on your own. The way y'all are going to be able to do this trick is that I'm going to show you, and then you'll be on the lookout for it. Right? So that's how this stuff works. I used to get really intimidated when I was learning stuff like this, and I would think to myself, man, I never would have thought of that. And it hadn't really dawned on me that my teacher didn't think of it either. Right? Somebody showed him. All right, so here's the trick. The trick is, drum roll, take the function two of whose level sets are your first two curves, call that u. Take the function two of whose level sets are your second two curves, call that v, and between the two of them, they will give you a fantastically convenient change of variables function. That's the trick. I did not think of it on my own, right? This is what you want to remember. This is the foot in the door that makes it all work. All right. Now, very important, these do have to be level sets. So you'll notice equals constant on the right. If the equations come to you and they're not written as level sets, then rewrite them as needed, right? But this trick only works if we have constants on the right-hand side. Well, it's a slight overstatement. This trick works best when you have constants on the right-hand side. All right, is everybody clear on the requirements? Yeah.
What if we have 3 different curves?
Then you might have to tweak this method or something like that. Yeah. So let me not be excessively rigid, right? But if you want it to work structurally identical to what I'm doing here, then it's got to be just so. Right? But yeah, I'm sure there are tweaks that will work in different situations. Okay, so now let's talk about why, right? Why is it so important that these be level sets? Who cares if these are constants on the right? And what's the deal with, choosing your change of variables function to be exactly, these two functions whose level sets we're looking at? Well, let's think about certain curves, and in particular, let's think about this first curve, xy equals 1. Here it is, xy equals 1. What is its image over on the left side going to look like? Well, if its equation is xy equals 1, and if xy is u, then its image is just going to be u equals 1, which is a perfectly vertical line, which we love because it's easy. Does that make sense? Right? Yeah. Uh-huh.
So in essence, is that just going to simplify our bound?
Yep, it dramatically simplifies our bounds. That's right. And so instead of having to deal with some wacky, ugly shape where I'm slicing and hitting corners and dealing with weird equations and reciprocals in my bounds and oh my gosh, all sorts of ugly, I get a nice, pretty little rectangle, which is awesome. Yep. Is that cool? Everybody happy? All right, so likewise for the other edges, I think you can persuade yourself with this as a sample that in fact this region, so this given region, its image in the UV plane is going to be, did I run out of colors? I'll use red, is this region here. Nice, pretty little rectangle. Everybody happy? Okay. So that is the motivation. Now we have a much nicer domain, and now it's just little details that we have to worry about. So let's think through those details. I am going to need a stretching factor. I am concerned about the fact that my function's going the wrong way. That's not the way it's supposed to go, right? But here's the thing. I can compute that stretching factor, taking the partials of u and v, because that's what I have formulas for. By the way, I'm aware we could solve for x and y. We could turn this function around. We could do it the old-fashioned way, but I want to demonstrate the method here, so let's ignore that we could solve for x and y. Let's just pretend we can't. Right? So I have formulas for u and v. I can write down the corresponding stretching factor, various partials, make a matrix, take the determinant, and that turns out to be this. So, per my argument above, if I want to know my stretching factor that I need, if I were able to solve for x and y and turn this around and make this change of variables function go the right way, right? What would my stretching factor be? No problem. It's just the reciprocal. Just like the notation suggests. Is everybody on board? Yes?
If we're not given like equations as level sets, how will we know if this is going to be helpful technique?
Play with it. Yeah. You gotta. So if you have various equations given to you, you want to think in terms of how can I manipulate these equations around in such a way that this will be nice. That it'll be level sets of a pair of functions that I can make work. And sometimes you can, in which case, great, go ahead. And sometimes you can't, in which case, well, this method only works sometimes. So yeah. Is that satisfying? Yeah. Is everybody happy? All right. Now, we are going to proceed. There is one remaining bump in the road that we are going to have to deal with, but let me just kind of get the ball rolling here. Reminder on our original domain here. Our integral was this. We were looking for an integral of x to the 8th y cubed. Okay. Well, here it is, x to the 8th y cubed. That's what I want to compute. The whole big idea is I wanted to rewrite this in terms of u's and v's. And so let's make that switch. And most of the work there is going to be in figuring out how to rewrite dx dy. And here's another place that this notation does some really nice things for us. Now, I'm going to confess that when I do questions that are like this, it can be a little confusing. Which way am I supposed to go again? And I want to go in the direction that's the opposite of what I want to actually do. So in some sense, I want to go in the wrong direction, but if it's set up in the wrong direction, then I want to go in the wrong of the wrong direction. You can get really turned around. It's very easy to get confused, right? So good news, the notation will keep track of that for you, right? As follows. If I want to turn dx dy into something times du dv so that I can do an integral in the uv plane, just think about which direction does this fraction need to go. Think about the faux cancellation. Again, I get the willies when I do that, right? But willies or not, this will always point you in the right direction. This will do the work for you of, do I need partial xy, partial uv? Wait a minute, do I need partial uv, partial xy? Which way does it go? It goes whichever way makes the faux cancellation work. Let the notation do your bookkeeping for you. Does that make sense? Everybody happy? All right, sweet. So apparently I need partial xy, partial uv, as I've already computed. And so that is just this, and we're in business. And here's what our integral has turned into right here. Okay, now there's one remaining problem. I need to figure out how to convert that integrand into u's and v's. It's currently in terms of x's and y's. Okay, so I guess I need to find the formula for x and the formula for y and plug those in. But wait a minute, that was kind of the whole point of this example, is that I don't know x and y. I don't have formulas for x and y. The whole point here is I'm going the other direction. So the subtle answer here is, in fact, I don't need x and y. Specifically, all I need is x to the 7th times y. Whatever this new integrand is that has every stretching factor and everything all sort of included into one expression, that is what I need to rewrite in terms of u and v. And thus begins a game. It's a different game every time. It'd be nice if there was a single algorithm that would always do this for us, but there isn't. This is just, it is what it is. So I'm going to show you how I deal with the little game in this particular circumstance, right? And you just got to keep in mind you're going to have to sort of tweak this approach with every example. They're all a little bit different, right? So here's what I figured. I have a product of powers of x and y. I want to rewrite that in terms of u and v, and let's not forget that's u and that's v, which you will notice themselves are also products of powers of x and y. Right, so here's the question before us. What would I guess? This question mark indicates I'm guessing here, right? But what would I guess would be a relationship that turns products of powers of x and y into another product of powers of x and y? And the game begins. All right? So what would you speculate you would do to products of powers to turn them into a product of powers? And here's my guess. I think I would take a product of powers of those products of powers, and the result would be a product of powers, and I might be able to negotiate these constants around in such a way as to make it actually the product of powers that I want. Now, that's a guess, right? That's a speculation. What we have in blue here is my change of variables function. What we have in green here is my resulting integrand that I need to rewrite in terms of u's and v's. And what we have in purple is my guess of how I think that might be possible. Does that make sense? Do you all see the motivation for my guess here? Now again, it's going to be different every time, right? This expression over here might be a linear combination of x and y or something. And maybe the formulas for u and v might be linear combinations of x and y. And then you would make a different guess as to what the structure, the purple structure, would be. So anyway, you can play algebra games and work out and determine what these constants a and b are. And once you found a and b, then you can rewrite your integrand. And once you've rewritten your integrand, if I can get this to cooperate, then that is what becomes my new integrand. And then we can just do with the question in the UV plane. That make sense? Everybody good? Okay. And I bet you we're out of time. And if we're not out of time, I'm sure I owe you the time. So we'll call it a day right here. And see y'all on Wednesday. Have a good one. And don't forget about attendance if I didn't already get you.